Hi, my name is Wesley Coe, and I am a biochemistry major from the class of 2019.
Hi, my name is Emily Waring, and I am a chemistry major from the class of 2019. We will be working through problem number 4 from chapter 13.3 in the general chemistry workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you have completed the problem, then we'll go over it together. To understand this problem, we will first need to understand the basic concepts of equilibrium and equilibrium constants. As you have discussed in class, equilibrium is the state in a reaction when both the forward and the reverse reaction are proceeding at the same rate. When a reaction is at equilibrium, we can define a quantity called the equilibrium constant, K, which describes the ratio of reactants and products present in a reaction at equilibrium. This value is defined as the product of the concentration of the products divided by the product of the concentrations of the reactants. Because it's simply a ratio, it's unitless. We can see from this expression that if K is greater than 1, there will be more products than reactants. Likewise, if K is less than 1, there will be more reactants than products. If a reaction is not yet at equilibrium, we are trying to determine which direction this reaction will proceed to get to equilibrium. We can use a quantity which we call Q, the reaction quotient. Q is calculated in the same way we calculate K, except the current concentrations of reactants and products are used rather than the concentration of reactants and products in equilibrium. If Q is greater than K, that means there are fewer reactants than there would be at equilibrium, and the reaction will proceed towards the reactants. Conversely, if Q is less than K, the reaction will proceed toward the products to reach equilibrium. Now that we have reviewed equilibrium, we can begin to solve the problem. An important thing to notice about this problem is the phases of the reactants and products. We can see in the reaction given that AgCl is a solid. This is important because in equilibrium constants, concentrations of solids and pure liquids are not included because they are not part of the solution and their concentrations do not change. A good strategy whenever we are dealing with an equilibrium reaction is to write out the expression for the equilibrium constant before you start looking in detail at the question. If we write out the equilibrium expression for this reaction, we will get K equals 1 over the concentration of silver times the concentration of chloride.
So let's look at part A. Silver nitrate is added to the equilibrium mixture. So looking at silver nitrate, we can tell that this is an ionic compound. And the thing we care about here is the silver plus ions that are going to be added to the solution when we add this ionic compound. If we think about raising the concentration of silver ions in the solution, we can write a Q expression and see that Q will be less than K because we have made the denominator larger. And since Q is less than K, the reaction will proceed in the product's direction. This connects the concept that you have probably learned about in class called Le Chatelier's principle. This principle states that if you put stress on one side of the equilibrium reaction, then the equilibrium will shift to the other side to relieve that stress. We can see this concept occurring in this problem since we are adding stress to the reactant side of the equilibrium. By adding more reactant, the equilibrium is shifting towards the products. You can apply this principle to solve the rest of the problem simply. So now let's move on to part B, adding potassium chloride to the reaction mixture. Part B is very similar to part A. We can solve this by writing out the Q expression or by using Le Chatelier's principle. If we want to use the Q expression, we should recognize that chloride is going to increase. This means that Q is less than K. So the reaction will proceed towards the products. We can also visualize this as we are adding stress to the reactant side of the reaction. And as a result, the reaction is shifting to make more products. Part C, adding solid silver chloride to the reaction mixture. Now, part C is a little bit different because we're talking about the solid product that is being created in this reaction. If we add solid product, we might expect that the reaction should move towards the reactants. But as you'll find, this is not the case. Because solids are not included in the equilibrium constant, if we write Q for the situation, we'll find that Q is actually equal to K. This means that the reaction will not change.
Now we'll move on to part D, adding ammonia to this reaction. It is important to recognize that ammonia is going to react with silver ions, removing them from solution. If we have a lower concentration of reactants, we will calculate that Q is greater than K. This tells us that the reaction will move towards reactants. If we wanted to think about this in terms of Le Chatelier's principle, we would see that we have created stress on the reactants by decreasing the amount of reactants. So to fix that stress, we will have to create more reactants to get back to equilibrium.
Thank you for listening to this video. If you have any further questions about this problem or these concepts, talk to an instructor or a study session leader.